Hello YouTube, my name is Neil. We're studying for the MCATs today. We're in the Physics and Math Review. Chapter 12, Data-Based Statistical Reasoning. Data-Based and Statistical Reasoning. Academic papers are extremely predictable. They generally begin with an abstract that reflects the major points of the rest of the paper. The author then provides an expanded introduction, materials and methods, data, and discussion. The key to a high-quality research paper is making this discussion unnecessary. Any scientist, when given the prior sections, should be led to the same conclusions as those given by the author. The test makers are keenly aware of this fact. On test day, you may be presented with research in the form of an experiment-based passage, and part of your task will be inferring the important conclusions that can be supported by the findings of the study. This chapter covers the last of the scientific inquiry and reasoning skills tested on the MCAT. The statistical analysis of raw data, interpretation of visual representation of this data, and application of data to answer research questions. We'll begin by examining basic statistical principles like distribution types, measures of central tendency, and measures of distribution. We'll also discuss probability and the semantics of this branch of mathematics. We'll conclude our discussion of probability and statistics with an exploration of statistical significance in basic hypothesis testing and confidence intervals. Then we'll move on to the interpretation of charts and graphs. Finally, we'll link all this information with the skills we gained in the last chapter and assess the future use and validity of studies. Measures of central tendency. Measures of central tendency are those that describe the middle of a sample. How we define middle can vary. Is it the mathematical average of the numbers in the data set? Is it the result in a data set that divides the set into two, with half the sample values above this result and half the samples below? Both of these data can be important, and the difference between them can also provide useful information on the shape of a distribution. Mean. The mean or average of a set of data, more accurately the arithmetic mean, is calculated by adding up all the individual values within the data set and dividing the result by the number of values. Should we write this down? I think we kind of know how to do an average, but let's write it down anyways. X equals the sum of all xi from I equals 1 to n, and that's set divided by n, where xi to xn are the values of all the data points in the set, and n is the number of data points in the set. As we discussed in the last chapter, the mean may be a parameter or a statistic, as is true of all the measures of central tendency, depending on whether we are discussing a population or a sample. Mean values are a good indicator of central tendency when all of the values tend to be fairly close to one another. Having an outlier, an extremely large or extremely small value compared to the other data values, can shift the mean towards one end of the range. For example, the average income of the United States is about $70,000, but half of the population makes less than $50,000. In this case, the small number of extremely high-income individuals in the distribution shifts the mean to the high end of the range. Following data were collected on the ages of attendees at Ray's birthday party. What is the mean age of the attendees? Is this an appropriate measure for this data? Well, 23 plus 22 plus 25 plus 22 plus 22 plus 24 plus 36 plus 20, and there's 1, 2, 3, 4, 5, 6, 7, 8. Divided by 8. 23 plus 22 plus 25 plus 22 plus 22 plus 24 plus 36 plus 20 divided by 8. 24.25. That's what they got. Because the mean is relatively near most of the values collected for this data set, it may be appropriate. Keep in mind, though, that the presence of an outlier and the fact that the mean is greater than all but 2 of the values collected indicates that the mean has been shifted toward the high end of the range. The presence of a single outlier does not invalidate the mean, but it does make interpretation in context necessary. So I guess in this case, 36 is the outlier. Median. The median for a set of data is its midpoint, where half of the data points are greater than the value and half are smaller. In data sets with an odd number of values, the median will actually be one of the data points. In data sets with an even number of values, the median will be the mean of the 2 central data points. To calculate the mean, a data set must first be listed in increasing fashion. The position of the median can be calculated as follows. Median equals n plus 1 over 2. Easy enough. Where n is the number of data values. In a data set with an even number of data points, this equation will solve for a non-integer number. For example, in a data set with 18 points, it will be 18 plus 1 divided by 2, which equals 9.5. The median in this case will be the arithmetic mean of the 9th and 10th items in the data set when sorted in ascending order. Median tends to be the least susceptible to outliers, but may not be useful for data sets with very large ranges. The data between the largest and smallest data point, as discussed later in this chapter, or multiple modes. Very large ranges, which is the difference between the largest and the smallest, and modes. Using the same data from the last question, find the median age of the attendees. Comparing this value to the mean, is the median a better or worse indicator of central tendency in this sample? Well, I guess we got to order these. 20, 22, 22, 22, 1, 2, 3, and 23, 24, 25, and then 36. 1, 2, 3, 4, 5, 6, 7, 8. So I guess we would average these two values. Should be 22.5. I mean, median is therefore 22.5. The median is a better indicator of central tendency for this data than the mean of 24.25. The median is unaffected by the outlier and lies close to most of the values in the data set. One could improve the representativeness of the mean by excluding 36 from the data set, in which case the mean would be 22.6 while the median would be 22. So it is 22.5. If the mean and the median are far from each other, this implies the presence of outliers or a skewed distribution. As discussed later in this chapter, if the mean and median are very close, this implies a symmetrical distribution. The mode, quite simply, is the number that appears the most often in a data set. There may be multiple modes in a data set, or if all numbers appear equally, there can even be no mode for a data set. When we examine distributions, the peak represents modes. The mode is not typically used as a measure of central tendency for a set of data, but the number of modes and their distance from one another is often informative. If a data set has 2 modes with a small number of values between them, it may be useful to analyze these portions separately or to look for other variables that may be responsible for dividing the distribution into 2 parts. What types of data sets are best analyzed using the mean as a measure of central tendency? Data sets with few outliers, or data sets that are close together. Calculate the mean, median, and mode of the following data set. 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 numbers. We got 2 plus 4 plus 4 plus 21 plus 9 plus 6 plus 23 plus 23 plus 25. 117 divided by 9. The average will be 13, or the mean. Let's put these in order to figure out the mode. We'll start with 2, 4, 4, 6, 9, and then 21, 23, 23, and then 25. So 1, 2, 3, 4, 5 is going to be our median. And then the mode is the most common. So we got 2 4s and we have 2 23s. So our modes will be 4 and 23. Now we got a pretty wide distribution here. So is the average better or the median? Is hard to say. The average is greater than the median. Why does it say my OBS is disconnected? It says that I'm not connected to the network. So if that's a mistake, please forgive me for stopping, but I have a feeling that you probably can't see this right now. Can't connect to this network. That sucks. Hey there, sorry about that little internet issue, but it looks like we're back. Right. In this case, between 13 and 9, it doesn't really make too much of a difference. I like 13. Anyways, if the mean and the median are far from each other, this implies the presence of outliers or a skewed distribution. As discussed later in the chapter, if the mean and median are very close, this implies a symmetrical distribution. All right, mode. Oh wait, we already did this, right? Oh yeah, this was this that we were doing. Calculate the mean, median, and mode. Distributions. Often a single statistic for a data set is insufficient for a detailed or relevant analysis. In this case, it is useful to look at the overall shape of the distribution as well as specifics about how that shape impacts our interpretation of the data. The shape of this distribution will impact all of the measures of central tendency that we have already discussed, as well as some measures of distribution which we will examine later. Normal distributions. In statistics, we most often work with a normal distribution, shown in figure 12.1, even when we know that this is not quite the case. We can use special techniques so that our data will approximate a normal distribution. This is very important because the normal distribution has been solved in the sense that we can transform any normal distribution to a standard distribution with a mean of 0 and a standard deviation of 1, and then use the newly generated curve to get information about probability or percentages of populations. The normal distribution is also the basis for the bell curve seen in many scenarios, including exam scores on the MCAT. Skewed distributions are not always symmetrical. A skewed distribution is one that contains a tail on one side or the other of the data set. On the MCAT, skewed distributions are most often tested by simply identifying their type. This is often an area of confusion for students because the visual shift in the data appear opposite direction of the skew. A negatively skewed distribution has a tail on the left, whereas a positively skewed distribution has a tail on the right. Because the mean is more susceptible to outliers than the median, the mean of a negatively skewed distribution will be lower than the median, while the mean of a positively skewed distribution will be higher than the median. These distributions and their measures of central tendency are shown in figure 12.2. We have the negative skew and the positive skew, so the tail being on the right and on the left. Bimodal distributions. Some distributions have two or more peaks. A distribution containing two peaks with a value in between is called bimodal. As shown in figure 12.3, it is important to note that a bimodal distribution, strictly speaking, might have only one mode if one peak is slightly higher than the other. However, even when the peaks are of two different sizes, we still call the distribution bimodal. If there is sufficient separation of the two peaks or a sufficient small amount of data within the value region, bimodal distributions can often be analyzed as two separate distributions. On the other hand, bimodal distributions do not have to be analyzed as two separate distributions either. The same measures of central tendency and measures of distribution can be applied to them as well. How do the mean, median, and mode compare for a right skewed distribution? Well, if it's skewed to the right in the positive direction, then the mean will be greater than the median, and the mode will be even less. Is that right? Can data that do not follow a normal distribution be analyzed with measures of central tendency and measures of distribution? Why or why not? They can be, they'll just be skewed. What is the difference between normal and skewed distributions and bimodal distributions? Normal and skewed distributions still have one peak. Bimodal have two peaks, or multiple peaks. All right. Distributions can be characterized not only by their center points, but also by the spread of their data. This information can be described in a number of ways. Range is an absolute measure of the spread of a data set, while interquartile range and standard deviation provide more information about the distance that data falls from one of our measures of central tendency. We can use these quantities to determine if a data point is truly an outlier in our data set. The range of a data set is the difference between the largest and smallest values. So, it's pretty simple. We'll write that down anyways. Range is x max minus x min. Range does not consider the number of items of the data set, nor does it consider the placement of any measures of central tendency. Range is therefore heavily affected by the presence of data outliers. In cases where it is not possible to calculate the standard deviation for a normal distribution because the entire data set is not provided, it is possible to approximate the standard deviation as 1/4 of the range. All right. Interquartile range. Interquartile range is related to the median first and third quartiles. Quartiles, including the median Q2, divide data when placed in ascending order into groups that comprise 1/4 of the entire set. There is some debate over the most appropriate way to calculate quartiles. For the purpose of the MCAT, we will use the most common and simplest method. To calculate the position of the first quartile in a set of data sorted in ascending order, multiply n by 1/4. If this is a whole number, the quartile is the mean of the value of that position and the next highest position. If this is a decimal, round up to the next whole number and take that as the quartile position. To calculate the position of the third quartile, multiply the value of n by 3/4. Again, if this is a whole number, take the mean of this position and the next. If it is a decimal, round up to the next whole number and take that as the quartile position. The interquartile range is then calculated by subtracting the value of the first quartile from the third quartile. So, the IRQ, or interquartile range, is Q3 minus Q1. The interquartile range can be used to determine outliers. Any value that falls more than 1.5 interquartile ranges below the first quartile or above the third quartile is considered an outlier. So anything that falls more than 1.5 interquartile ranges. Okay. Using the interquartile range, determine whether the 36-year-old man is an outlier in this set. 20, 22, 22, 22, 23, 24, 25, 26. 1, 2, 3, 4, 5, 6, 7, 8. So, 8 divided by 4 is 2. The 2 position and the 3 position average is 22. And then 8 times 3/4 is going to be 6. So the 6th position and the 7th position averaged out would be 24.5. And so the interquartile range is 24.5 minus 22, which is 2.5. So is 36 an outlier? Well, is it more than 1.5 times this? So 3.75? Is it 3.75 away from above the third quartile? So 3.5 over 24.5. So 2.5 times 1.5 equals 3.75. And 24.5 plus 3.75 equals 27, 28.25. So 36 is an outlier because 36 is greater than 28.25. Is that what they did? They found the first quartile and the third quartile the way we did. The interquartile range is 2.5, and then they multiplied that by 1.5 to get 3.75, and that plus 24.5 to get 28.25. And since 36 is above 28.25, this is an outlier. All right. Standard deviation. Standard deviation. Give me a second. All right. Standard deviation is the most informative measure of distribution, but it is also the most mathematically laborious. It is calculated relative to the mean of the data. Standard deviation is calculated by taking the difference between each data point and the mean, squaring this value, dividing the sum of all these squared values by the number of points in the data set minus 1, and then taking the square root of the result. Expressed mathematically as, I think, sigma equals the sum of xi minus the average squared over n minus 1 and the square root of that whole thing. So yeah, that's kind of a beast, isn't it? Standard deviation, xi to xn are the values of the data points. X is the mean, n is the number of data points. N minus 1, we use n minus 1 instead of n is mathematically but not practically important, and the reason for doing so is beyond the scope of the MCAT. Okay, so you don't need to know why we use n minus 1. Calculate the standard deviation for the following data set. 1, 2, 3, 9, 10. So first we get a mean. So we'll go 1 plus 2 plus 3 plus 9 plus 10. Divided by 5. So average equals 5. Now we're going to subtract each value from 5. So I guess, we'll have negative numbers. 1 minus 5 is negative 4. 2 minus 5 is negative 3. 3 minus 5 is negative 2. 9 minus 5 is 4, and 10 minus 5 is 5. So each of those squared before we add them up, all right? So 16, 9, 4, 16, 25. They gave us nice easy numbers for this, didn't they? So should I mark down what we're doing here? This is xi minus x. This is xi minus x squared. Now the sum of all those is 16 plus 9 plus 4 plus 16 plus 25 is 70. Divided by 4 is n minus 1 is 4. divided by 4 equals 17.5. So this is divided by n minus 1. And then the square root of all that should equal our standard deviation. So let's go to our scientific calculator and find the square root of 17.5 is just about 4.18. Let's see what they got. They got 4.18 as well. Keep in mind that when calculating the mean, we use n as the denominator, but when calculating standard deviation, we use n minus 1. All right. Made a nice little table here. That's handy, huh? We kind of did it informally. All right. The standard deviation can also be used to determine whether a data point is an outlier. If the data point falls more than 3 standard deviations from the mean, it is considered an outlier. The standard deviation relates to the normal distribution as well. On a normal distribution, approximately 68% of data points fall within 1 standard deviation of the mean, 95% fall within 2 standard deviations, and 99% fall within 3 standard deviations. As shown in figure 12.1 earlier. Integration or specialized software can be used to determine percentages falling within other intervals. Outliers. While we have already discussed methods for determining if a data point is an outlier, it is useful to know how to approach data outliers. Outliers typically result from one of 3 causes. 1, a true statistical anomaly, for example, a person who is over 7 feet tall. A measurement error, for example, reading the centimeter side of a tape measure instead of inches. A distribution that is not approximated by the normal distribution, for example, a skewed distribution with a long tail. When an outlier is found, it should trigger an investigation to determine which of these 3 causes applies. If there's a measurement error, the data point should be excluded from analysis. However, the other 2 situations are less clear. If an outlier is the result of a true measurement but is not representative of the population, it may be weighted to reflect its rarity, included normally or excluded from the analysis depending on the purpose of the study and pre-selected protocols. The decision to be made before a study begins, not once an outlier has been found. When outliers are an indication that a data set may not approximate the normal distribution, repeated samples or larger samples will generally demonstrate if this is true. Compare the method of determining outliers from the interquartile range and from the standard deviation. Interquartile range, it's 1.5 times greater than the interquartile range and above Q3 or below Q1. So if you have a distribution of data, supposedly this is supposed to be 1/4 and 3/4, and they're saying that this times 1.5, so longer than this, more than this, so that's unlikely. So yeah, that's a true outlier. For standard deviation, outliers are 3 standard deviations. And so 99% of the data is supposed to fall between 3 standard deviations. So you have something in the 1% here. Yeah, I don't know how you compare them. I don't know which one's better. How do range and standard deviation generally relate to one another mathematically? Is this relationship accurate for the data set used earlier in this section? How do range and standard deviation relate to one another mathematically? Well, range is just x max minus x min, and standard deviation is all the differences squared and added up and averaged out, kind of. So you could say that the range is kind of built into this. Are they supposed to be a similar number or anything? What's the range of this? 10 minus 1 is 9. For this data set, the range is 9, is much greater than the standard deviation. But what do they say? Our estimate of standard deviation could just be 1/4 the range. And that 1/4 of 9 is less than 4.18. Why would the average difference from the mean be an inappropriate measure of distribution? Why would the average distance difference from the mean be an inappropriate measure of distribution? I mean, I guess by squaring and taking the square root, you knock out all the negative numbers. So if you had negatives on one side and positives on the other side, you have to square them out so that there are no negatives, I think. Let's see the answers to those. 12.3. Outliers can be identified as data points more than 1.5 times IQR below Q or above Q3. It can also be identified as data points more than 3 standard deviations above or below the mean. The cutoff values calculated through the two methods are likely to be different, and the selection of one method over another is of preference and study design. Standard deviation is superior. Where the data are not available, the range can be approximated as 4 times the standard deviation. For this data set, the relationship fails. The range is 9, which is only a little more than twice the standard deviation. This is because the data set does not fall in a normal distribution, right? The average distance from the mean will always be 0. This is why in calculations of standard deviation, we always square the distance from the mean and then take the square root at the end. It forces all of the values to be positive numbers, which will then cancel out to 0. Which will not cancel out to 0. Right on. All right. Probability. Probability is usually tested on the MCAT in the context of a science question rather than being tested on its own. In particular, genetics questions involve the Hardy-Weinberg equilibrium and Punnett squares are common applications of probability. Probability also underlies statistical testing, which will be investigated in the next section. All right. Independence, mutual exclusivity, and exhaustiveness. In probability problems, we must first determine the relationship between events and outcomes. For events, we are most interested in independence or dependence. Conceptually, independent events have no effect on one another. If you roll a die and get a 3, then pick it up and roll it again, and the probability of getting a 3 on the second roll is no different than it was before the first roll. Independent events can occur in any order without impacting one another. Dependent events have an impact on one another, such as the order changes the probability. Consider a container with 5 red balls and 5 blue balls. The probability that one will choose a red ball is 5 out of 10. If a red ball is indeed chosen, then the probability of drawing another red ball is 4 out of 9. If, however, a blue ball is chosen, then the probability of drawing a red ball is 5 out of 9. In this way, the probability of a second event getting a red ball on the second draw is indeed dependent on the result of the first event. We are also concerned with whether events are mutually exclusive or not. This term applies to outcomes rather than events. Mutually exclusive outcomes cannot occur at the same time. One cannot flip both heads and tails in one throw, or be both 10 and 20 years old. The probability of two mutually exclusive outcomes occurring together is 0. Finally, we must consider if a set of outcomes is exhaustive or not. A group of outcomes is said to be exhaustive if there are no other possible outcomes. For example, flipping heads or tails are said to be exhaustive outcomes of a coin flip. These are the only two possibilities. Calculations. For independent events, the probability of two or more events occurring at the same time is the product of their probabilities alone. So let's write this down. The probability of A and B equals the probability of A times the probability of B. For example, the probability of getting heads on a coin flip twice in a row is the same as the probability of getting heads the first time times the probability of getting heads the second time. So 0.5 times 0.5 equals 0.25. The probability of two independent events occurring is shown diagrammatically in figure 12.4. The probability of at least one of two events occurring is equal to the sum of their initial probabilities minus the probability that they will both occur. So the probability that either A or B will happen is the probability of A plus the probability of B minus the probability of A and B. In certain populations, 10% of the population has diabetes. 30% is obese. If 7% of the population has both diabetes and obesity, are these events independent? If 7% of the population has both diabetes and obesity, are these events independent? Are they independent, having diabetes and obesity? I don't think they are, but I mean, in this case, they are, right? If one chose an individual at random from this population, what would be the probability of that patient having at least one of the two conditions? 7% has both, but they're independent, so we're going to ignore that one. What would be the probability of having at least one of the two conditions? So we're going to do the OR calculation, and to do that, first we have to do an AND calculation anyways. So P, A, and B equals the probability of A, which is 10, or 0.1, times the probability of B, 0.3. Yeah, I don't need that. Right? 0.3 times 0.1 is 0.03. Basically dividing by 10. And then P, A, or B is going to equal 0.1 plus 0.3 minus 0.03, which equals 0.1 plus 0.3 minus 0.03. 0.37. So the probability of having one or the other. Why are they calculated to be 0.07 and not 0.03? 0.1 times 0.3. With the numbers given, these events cannot be independent. For independent events, PA and B equals PA times PB, which equals P having diabetes, P being obese, 0.03. In this population, the probability of having diabetes and being obese is 0.07. So the probability of having both is higher than it should be, which implies that it's not independent, that it's dependent. So instead of using this 0.03, we're going to use the 0.07 that they give us, is what they're saying. So instead of 0.37, it'll be 0.33. And that's what they have, 0.33. All right. So we're not going to do that one. All right. Assume the likelihood of having a male child is equal to the likelihood of having a female child. In a series of 10 live births, the probability of having at least one boy is equal to, well, each one is 1 over 5. At least one boy is going to be 1 over 2, not 1 over 5, 1 over 2, plus 1 over 2, plus 1 over 2, plus 1 over 2, plus 1 over 2. Is that right? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So that's just adding them up. But I have to subtract, because then I get more than 1. So I have to subtract the probability of all of them, I guess. Probability of A plus B plus, so say it's A plus B plus C plus D, 10 of them, minus all of them. That's a small number, all of them. 0.5 times 0.5. Right, like I'm just subtracting 0.001 away from that 5. Yeah, can you have a probability greater than 1? Find the following terms: independence, mutual exclusivity, and exhaustiveness. Independence means that the outcome of one doesn't affect the outcome of the other. Mutual exclusivity means that they can't both happen. And exhaustiveness means that all the choices are accounted for, all the possibilities are accounted for. So let's find out what the chance of having one boy out of 10 is. 12.4 is simplify this question by rewording it as the probability of not having all girls. Having at least one boy and having all girls are mutually exclusive events, and no other possibilities can occur. Thus, the probability of having all girls is 0.5 to the 10th power, and the probability of having at least one boy is 1 minus 0.5 to the 10th power, or 99.9%. There you have it. And how do they do that? One minus 0.5 to the 10th power, 99.9. All right. Statistical testing. Hypothesis testing and confidence intervals allow us to draw conclusions about populations based on our sample data. Both are interpreted in the context of probabilities and what we deem to be an acceptable risk of error. Hypothesis testing. Hypothesis testing begins with an idea about what may be different between two populations. We have a null hypothesis, which is always a hypothesis of equivalence. In other words, the null hypothesis says that two populations are equal, or that a single population can be described by a parameter equal to a given value. The alternative hypothesis may be non-directional, that the populations are not equal, or directional. For example, that the mean of population A is greater than the mean of population B. The most common hypothesis tests are Z or T tests, which rely on the standard distribution or the closely related T distribution. From the data collected, a test statistic is calculated and compared to a table to determine the likelihood that that statistic was obtained by random chance, under the assumption that our null hypothesis is true. This is our p-value. We then compare our p-value to a significance level. 0.05 is commonly used. If the p-value is greater than alpha, then we fail to reject the null hypothesis, which means that there is not a statistically significant difference between the two populations. If the p-value is less than alpha, then we reject the null hypothesis and state that there is a statistical significance between the two groups. Again, when the null hypothesis is rejected, we state that our results are statistically significant. The value of alpha is the level of risk that we are willing to accept for incorrectly rejecting the null hypothesis. This is also called a type 1 error. In other words, a type 1 error is the likelihood that we will report a difference between two populations when one does not actually exist. A type 2 error occurs when we incorrectly fail to reject the null hypothesis. In other words, a type 2 error is the likelihood that we report no difference between two populations when one actually exists. The probability of a type 2 error is symbolized by beta. The probability of correctly rejecting a false null hypothesis, reporting a difference between two populations when one actually exists, is referred to as power and is equal to 1 minus beta. Finally, the probability of correctly failing to reject a true null hypothesis, reporting no difference between two populations when one does not exist, is referred to as confidence. These conditions are summarized in 12.1. So, reject the null hypothesis when you shouldn't have is a type 1 error. Fail to reject it when you should have, or fail to reject it when it is true, that's confidence. Rejecting it when it's not true, rejecting the null hypothesis when it's not true, that's power, and failing to reject it when it is not true is a type 2 error. All right. So in the way that power is 1 minus beta, is confidence 1 minus alpha? Let's find out. Confidence intervals are essentially the reverse of hypothesis testing. With the confidence interval, we determine a range of values from the sample mean and standard deviation. Rather than finding a p-value, we begin with a desired confidence level, 95% is standard, and use a table to find its corresponding z or t score. When we multiply z or t score by the standard deviation, and then add and subtract this number from the mean, we create a range of values. For example, consider a population for which we wish to know the mean age. We draw a sample from that population and find that the mean of the sample is 30, with a standard deviation of 3. If we wish to have 95% confidence, the corresponding z-score, which would be provided on test day, is 1.96. Thus, the range is 30 minus 3 times 1.96 to 30 plus 3 times 1.96. So 24.12 to 35.88. We can then report that we are 95% confident that the true mean age of the population from which this sample is drawn is between 24.12 and 95.88. All right. How do hypothesis tests and confidence intervals differ? Confidence intervals are kind of the reverse of the hypothesis test, right? Rejecting the null hypothesis, we want like a low error, I guess, or, right, is alpha literally, or significance level? So yeah, if the p-value is less than some number 0.05, then we reject the null hypothesis. And this is just kind of like the inverse of that, right? Like if we have a high confidence, that's like rejecting the null hypothesis, I guess. And it does look like it's related, right? Like that 0.05 is 1 minus 0.95, right? All right, if the p-value is greater than alpha in a given statistical test, what is the outcome of the test? If the p-value is greater, then we fail to reject the null hypothesis. How is the p-value calculated during a hypothesis test? The p-value is calculated, that's a good question. From a data collected, a test statistic is calculated compared to a table to determine the likelihood of that statistic. Do they tell us how to find the p-value? Do they tell us how to find the p-value? They don't tell us that. So I don't know how you're supposed to know that. True or false? Power is the probability of correctly rejecting the null hypothesis. I guess so. Yeah, that's right. I'd say that's true. It's technically 1 minus the probability of failing to reject the null hypothesis. But I guess that is, the same thing, right? Let's check these answers. Make sure we're on point. 12.5. Hypothesis tests are used to validate or invalidate a claim with two populations are different, or that one population differs from a given parameter. In a hypothesis test, we can calculate a p-value and compare it to the chosen significance level to conclude if an observed difference between two populations is significant or not. Confidence intervals are used to determine a potential range of values for the true mean of a population. 2. If the p-value is greater than alpha, then we fail to reject the null hypothesis. After the test statistic is calculated, a computer program or table is consulted to determine the p-value of the statistic. Their answer is use a computer. Okay. And then finally, true. Power is the probability that the individual rejects the null hypothesis when the alternative hypothesis is true for that population. Great. Charts, graphs, and tables. All right. Because your career will be filled with evidence-based medicine, it is important to be able to recognize and interpret data in multiple forms. We have already considered the mathematical side of statistics. Now let's take a look at the visual side. On the MCAT, anticipate that most passages in the sciences will be accompanied by a visual aid in some way. Frequently, this will be a chart, graph, or data table. Pie or types of charts. Charts represent information in a visual format and are frequently used for categorical data. Pie or circle charts are used to represent relative amounts of entities and are especially popular in demographics. They may be labeled with raw numerical values or with percent values. The primary downside to pie charts is that as the number of represented categories increases, the visual representation loses impact and becomes confusing. For example, in figure 12.5, the population of each of the 50 states and the District of Columbia is presented on a pie chart, but the large number of entities make the graph incoherent. I guess so, yeah, you can't really understand much from this because there's just too many pies, huh? I mean, you can see that California and Texas are big, and Delaware and South Dakota are small. All right. Bar charts and histograms. Bar charts and histograms are likely to contain significantly more information than a pie chart for the same amount of page space. Bar charts are used for categorical data, which sort data points based on predetermined categories. The bars may be sorted by increasing or decreasing bar length. The length of a bar is generally proportional to the value it represents. Wherever possible, breaks should be avoided in the chart because of the potential to distort scale. To that end, be wary of charts that contain or graphs that contain breaks. They may be enlarging the difference between bars. 12.6 shows a representative bar graph for causes of cancer death in the United States in 2010. Histograms represent numerical data rather than discrete categories. Histograms are particularly useful for determining the mode of a data set because they are used to display the distribution of a data set. Show us a picture of a histogram. Okay. Box plots are used to show the range, median, quartiles, and outliers for a set of data. A labeled box plot is called a box and whisker. Box plot. The box of a box and whisker plot is bounded by Q1 and Q3. Q2, the median, is the line in the middle of the box. The end of the whiskers correspond to maximum and minimum values of the data set. Alternatively, outliers can be presented as individual points, with the ends of the whiskers corresponding to the largest and smallest values in the data set that are still within 1.5 IQR of the median. Box and whisker plots are especially useful for comparing data because they contain a large amount of data in a small amount of space, and multiple plots can be oriented on a single axis. Maps. In addition to the other forms of charts, data can be illustrated geographically. Maps of health conditions, population density, political districts, and ethnicity are relatively easy to comprehend and may show geographic clustering for some data. The best map data will examine one or at most two pieces of information simultaneously. Any further data may inhibit clarity. A map of population density in each country of the world is shown in 12.8. Graphs and axes. While we're all familiar with constructing graphs, especially scatter plots and line graphs, it is important to know some important features and potential stumbling blocks of graphs as we move toward test day. When presented with a graph, you should attempt to draw rough conclusions immediately, but should not spend time analyzing all of the details of the graph unless asked to do so by a question. The first thing to do when you encounter a graph on test day is to look at the axes. Linear graph. Linear graphs have the relationship between two variables. They generally involve two direct measurements and, strictly speaking, do not have to be a straight line. The shape of the curve on this type of graph may be linear, parabolic, exponential, or logarithmic. These are shown in figure 12.9. On test day, you should be able to recognize at least these four shapes of graphs: linear, parabolic, exponential, and logarithmic. The axes of a linear graph will be consistent in the sense that each unit will occupy the same amount of space. The distance from 1 to 2 to 3 to 4 on each axis remains the same size. As with bar graphs, be wary of scale and breaks in axes. Where both the shape of the graph and the graph type are linear, we should be able to calculate the slope of the line. Slope m is the change in the y direction divided by the change in the x direction for any 2 points. M equals change in y over change in x. Calculate the slope of the line in the graph shown below. Well, we start at 5, 1, 1.5, 1.6, 5.6. Negative 1.65. So y changed 1.65, and in that amount of time, 2, 4, 5. X changed, went up 5. I switched x and y. Y is 5. X changed by 1.65. Let's change that around. Which is around 3, they're saying. All right, slope of 3. All right, semi-log and log-log graphs. Semi-log graphs are a specialized representation of a logarithmic data set. They can be easier to interpret because the otherwise curved nature of the logarithmic data is made linear by a change in the axis ratio. In semi-log graphs, one axis, usually the x-axis, maintains the traditional unit spacing. The other axis assigns spacing based on a ratio, usually 10, 100, 1000, and so on. The multiples may be of any number as long as there is consistency in the ratio from one point on the axis to the next. Figure 12.10 shows an example of a semi-log plot. So while these increment by 1, this increments by a factor of 10. In some cases, both axes can be given a different axis ratio to create a linear plot. When both axes use a constant ratio from point to point on the axis, this is termed a log-log graph. Note that the difference between these three plot types, linear, semi-log, and log-log, is based on the labeling of the axis. Therefore, it is crucial to pay attention to the axis on test day to be able to interpret the graph correctly. Interpreting tables. Unlike with graphs, you should only take a brief moment to glance at the title of a table before approaching test day questions. Tables are more likely to contain disjointed information than either charts or graphs because they often contain categorical data or experimental results. Tables that do not have unusual data values, zeros, outliers, changes in a trend, and so on, should be approached especially briefly. When a table does contain significant organization, for example, listing results progressively, this structure is likely to be relevant while answering questions. For example, a trend that suddenly appears or disappears will often require an explanation. Additionally, when provided with data in the form of a table, you should be able to convert it to a rough graph or to a linear equation. The MCAT may test on the interpretation of slope without actually providing a graph. What type of data relationship is least likely to require transformation into a semi-log or log-log plot? What type of data relationship? Linear relationships are least likely to need logarithmic plots. Fill in the following table with the pros and cons of each type of visual data representation. Pie chart, pro, it's good at comparing. Con, can't have a lot. Bar graph, I don't know what the pro is for a bar graph. Categorical data, B, I guess, avoid breaks and distortion of scale. Box plot, lots of information. What's the downside of box plots? They don't give us one. I don't know, you could say it takes longer to look at and understand. Map. Pros, shows data geographically. Con, you can't have many data points. 1 or 2 is the max. Graph. Graphs are great for the relationship of 2 variables. You can calculate slopes and whatnot. Cons, I don't know, maybe it's not good if you have more variables or time-consuming to create and understand. Table. Table usually has superfluous information. So that would be a con. Pro, I don't know, point out trends. It's good for categorical data, I guess. How do exponential and parabolic curves differ in shape? Exponential grows. Parabolic also grows, but it's symmetrical, while exponentials just start low and grow. Let's see what they say about these pros and cons. Linear relationships can be analyzed without any data or acts of transformation to semi-log or log plots. Right. Linear relationships don't need logarithmic charts. Pie chart. Easily constructed, useful, overwhelmed with multiple categories. Bar graph, good for large categorical data sets. Axes can be misleading. Box plot, information dense, may not highlight outliers. Only useful for numerical data, if you say so. Map, provide relevant geographic information. Only 2 variables at a time. Graph, useful for estimation, provide relationships. Axis labels and logarithmic scales require careful interpretation. Okay, they require interpretation. Table, categorical data, can be represented without comparison. Does not require estimation for calculations. Can be disorganized and unrelated. All right. Oh yeah, and the exponential and parabolic curves both have a steep component. However, exponential curves have horizontal asymptotes because become flat on one side, while parabolic curves are symmetrical and have steep components on both sides of a center point. All right. Applying data. Finally, we have reached the discussion section of an academic paper in which the data that we have gathered and interpreted is applied to the original problem. We can then begin drawing conclusions and create new questions based on our results. Because much of this was covered in the discussion on experimental methods in Chapter 11, we will be terse in our review here. Correlation and causation. As discussed previously, we must be careful with our wording when discussing variable relationships. Correlation refers to a connection. Direct refers to a connection, direct relationship, inverse relationship, or otherwise between data. Correlation does not necessarily imply causation. We must avoid this assumption when there is insufficient evidence to draw such a conclusion. If an experiment cannot be performed, we must rely on Hill's criteria discussed in Chapter 11. Remember that the only one of Hill's criteria that is uniformly necessary for causation is temporality. In the context of scientific knowledge, when interpreting data, it is important that we do not state the apparent relationship between data, but also begin to draw a connection to other concepts in science and to our background knowledge. At a minimum, the impact of the new data on the existing hypothesis must be considered. Although ideally, the new data would be integrated into all future investigations on the topic. Additionally, we must develop a plausible rationale for the results. Finally, we must make decisions about our data's impact on the real world and determine whether or not our evidence is substantial and impactful enough to necessitate changes in understanding or policy. True or false? Statistical significance is sufficient criteria to enact policy change. False. True or false? Two variables that are causally related will also be correlated with each other. True. I think causation precedes correlation. Let's double check those. False and true. Right on. All right. Discrete practice questions. Let's get right into it. 1. Which of the following outliers would most likely be the easiest to correct? A typographical error in data transfer, a measurement error in instrument calibration, a heavily skewed distribution, or a correctly measured anomalous result? So the correctly measured anomalous result, you have a decision to make whether to include that or not. Heavily skewed distribution, same thing. A measurement error in instrument calibration will require fixing the instrumentation. A typographical error, on the other hand, you don't have to go back to the experimental step. You could just take it out. I think A is probably the easiest. In a sample of hospital patients, the mean age is found to be significantly lower than the median. Which of the following best describes the situation? So they said the mean is lower than the median. So there's an outlier, a young outlier. It's skewed left. 2B. 3. What is the median of the following data set? Median of 7 plus 17 plus 53 plus 23 plus 4 plus 2 plus 4 equals 110. I'm going to write this out just so you can see what we're doing here. One, 2, 3, 4, 5, 6, 7 divided by 7. 15.71. 15.7. Great. 3. C. 4. A hypothesis test was correctly conducted and the experimenter failed to reject the null hypothesis. Which of the following must be true? The p-value was, so if the p-value is greater than alpha, you failed to reject the null hypothesis. So p-value is greater than alpha. A type 1 error did not occur. What was that type 1 error again? Type 1 error, rejecting the null hypothesis when the hypothesis is true. So it means a type 1 error did not occur. The power of the study was too small. If the power The power should be large. Alpha should be small. Power should not be small. Right? The probability of correctly rejecting a false null hypothesis. You want that number to be large. So not 3, but 1 and 2 look good to me. I think I'll go with C. A 95% confidence interval will fall within what distance from the mean? I think 3 standard deviations, right? Oh no, 2 standard deviations, because 3 is supposed to be 99%. No, this is confidence. This isn't the data. The 99% of the data should fall between 3 standard deviations. But of the confidence interval, it is 3 standard deviations for 95%. 5C. 6. Are there any outliers in the following box plot? Doesn't look like it. Would you call these outliers? I guess we have the Q1 and 3 here, and 1.5. So even if I doubled this, it still wouldn't fit in here. So this does look like an outlier. On the other hand, this doesn't look like an outlier. We could quickly calculate it. We can go 2280 minus 2075. So that's 205 times 1.5 is 307.5. So 2280 plus 307.5. 26 is also outside. So both 1575 and 2600 are outliers. Fascinating. 6C. That again. What did we do there? We did 2280 minus 2075. 2280 minus 2075 equals 205 times 1.5 times 1.5 equals 307.5. So that plus 2075 is 2382. So our values should fall between that and 2280 minus 307.5. 1972.5. And 1575 is on the outside of that interval, and 2600 is also on the outside of that interval. What did I do? I just messed that up. I switched these two. Let's do that again. Two 280 plus 307.5. 25. The high end of our interval is 2587.5, and 2075 minus 307.5. 1767.5. This is our interval. Both of the numbers are outside. All right. Number 7, the following titration curve is an example of a sigmoidal relationship on a log-log graph, a sigmoidal relationship on a linear graph, a logarithmic relationship on a semi-log graph, a logarithmic relationship on a log-log graph. Volume is not logarithmic. pH is logarithmic. So it would be a semi-log graph. But they're calling this a logarithmic relationship? Okay. Looks sigmoidal to me. But I know it's not a log-log or a linear graph. And I know it's a semi-log graph, so I'm just going to go with C. 7. C. 8. Assume that blonde hair and blue eyes are independent recessive traits. If one parent is a carrier for each gene, while the other parent is homozygous recessive for both genes, what is the probability that the first two offspring will both have blonde hair and blue eyes? So, blonde hair and blue eyes are independent. One parent is a carrier for each gene. So, heterozygous. So let's say it's one parent. Should we do a little Punnett square? There's one parent, there's the other parent. Whoops. What is the probability that the first two offspring will both have blonde hair and blue eyes? So does being a carrier make you have it? Nobody's capital BB, so I'd say nobody has it. But that's not an option. So, I guess being heterozygous makes you have it. So the question is, how many are heterozygous? So for each of the conditions, you have a Punnett square like this. So for each of the conditions independently, it's 50-50. You got to multiply that together for them both happening. So the possibility of one plus the possibility of the other minus the possibility of both, I guess. Minus 1 over 4. So 1 minus a fourth, 75%? That's not an option. 25% is an option. So if we don't do this having both, maybe if it's independent, you don't have to subtract having both. Because this is just a nice 1/4. Let's go with B since it's an option. I don't see that. Yeah, that'll do. Number 9. Based on the country level map below, which of the following statements best represents the data about elderly individuals? Note, the darker the shade of green, the higher the percentage of elderly persons in the country. A, what are we doing? Which of the following statements best represents the data? Okay. Most of the elderly people in the United States live in the center of the country. Most of the people living in the center of the United States are elderly. The center of the United States tends to have a larger portion of elderly people. There are more elderly people moving to the center of the country than elsewhere. So we don't know about moving. We don't know change over time. So let's cut D out. The center of the United States tend to have a larger portion of elderly people. That sounds true. Because percentage of elderly people. Darker shade of green, the higher the percentage of elderly persons in the county. Most of the elderly people in the United States live in the center of the country. We just know proportions. We don't know that. And most of the people living in the center of the United States are elderly. We also don't know the not elderly. Well, I guess, yeah. I guess we don't know numbers. We can't say more than 50 or less than 50. We just have these relative values, these colors, darker versus lighter. I like C. C sounds the most accurate to me. 10 is the confidence level. As the confidence level increases, a confidence interval. As the confidence level increases, a confidence interval becomes thinner or becomes wider. I think it actually becomes smaller, right? Because you don't want a huge confidence interval. You want a small confidence interval, right? No, you want a high confidence level. As the confidence level increases, a confidence interval. So confidence of 95% is this confidence interval. Our confidence so they don't tell us how confidence interval affects that number, this 1.96, the z-score. If we wish to have a 95% confidence, the corresponding z-score, which would be provided on test day, is 1.96. So I think the confidence interval must be smaller. That just makes more sense, right? Because that if you have a wider range, then it's less accurate, kind of. If it's a smaller range, then it's more accurate. So I'd say a higher confidence just makes sense to have a smaller interval. So I'm just going to go with B. We'll find out. Which of the following measures of distribution is most useful for determining probabilities? Range, average distance from mean, interquartile range, standard deviation. Standard deviation, right? They just said that's the most accurate period, so right. 12. It is known that crickets increase their rate of chirping in a direct linear relationship with temperature until a maximum chirp rate is reached. Which of the following graphs best represent this relationship? So increasing and then steady. Now what's the difference between this and this? 2, 4, 8, 16, 32. This is logarithmic. So this is not really linear. This is linear and linear. So that's linear. 12's got to be B. A new medication for heart failure is being developed and has had a statistically significant effect on contractility in clinical trials. Which of the following would not likely cause the drug to be held back from common use? The value of alpha used was 0.5. Similar compounds display toxicity. The effect size is clinically insignificant. The study had low power to detect a difference. Do we want power or we don't want power? We want power, right? Power, yeah, we want power. So what will prevent it? Having low power, having a high alpha. Similar compounds display toxicity. The effect is clinically insignificant. So that would, having low power to detect a difference would. Value of alpha used was 0.5. I mean, that's a personal choice, right? I'd say 13 is least likely to cause a drug to be held back. All the other ones do look like they would hold the drug back. The following histogram contains a bimodal distribution. No. Yeah, sure. It goes down and then comes back up. Should be analyzed as two separate distributions. It contains one mode. It has one mode, that's true. It contains a bimodal distribution, that's also true. So 1 and 3 should be analyzed as two separate distributions. I don't think it has to be. In this case, that depends on the case, right? In this case, I'd only say 1 and 3 are correct. 14, C. 15. Which of the following values correspond to the probability of a type 1 error? Alpha, right? Type 1 error, it's got to be alpha. 15, A. Let's see how we did. 1, A, 2, B. 3, they said it was B, not C. 3B. The median is the central data point in an ordered list. Because this data set of numbers is a central point. Did I go with mean instead of median? Oh, shoot. What is the median? I assumed that they wanted the mean. We did this wrong. Should have just put it in order. 2, 4, 4, 7, 17, 23, 53. And so between 7 and 17 there. Just what? 2, 4, 4, 7, 17, 23, 53. 1, 2, 3, 4, 5, 6, 7. So yeah. 7's your median. Oh, shoot. Silly mistake. Don't make silly mistakes. Number 4, C. 5 is B, not C. Approximately 95% of the value falls within 2 standard deviations. The confidence interval is constructed using the same values. Approximately 68% of the values are within 1 standard deviation, 99 are within 3 standard deviations. So it is 2 standard deviations. My mistake, I thought it was difference for confidence intervals, but it is the same as 3 standard deviations, the same as the values for the normal distribution. A confidence interval is constructed using the same values as the values for standard deviation. My mistake. 6C, 7B, not C. I said the first term in the answer choices describes the shape of the curve. While we did not discuss sigmoidal curves in this chapter specifically, they do show up in other places in science, in particular for enzymes, cooperative binding, and titration. Sigmoid curves are S-shaped. The second term refers to the type of plot. Because the axes have the same scale throughout, this is a linear graph. Note that even though the y-axis represents logarithmic changes in h, the actual unit used is pH, which increases linearly. So 7 is linear, sigmoidal, and linear. It's linear because while the negative log of h is logarithmic, pH is not. Shoot. Well, number 8 is A, not B. How do they do this? Because one parent is homozygous for both traits, we are only concerned with the other parent. This parent has a 50% chance of transmitting each independent trait, and thus a 25% chance of transmitting both. This probability is the same for both pregnancies because they are independent events. Thus, the probability that both children exhibit both traits is a quarter times a quarter, or 6.25%. So these are for the two traits, but they're two children. So we take that 1/4 and multiply it by another to get 6.25, or 1/8. No, 1/16 rather. Nine is C. 10 is A, not B. A, to increase the confidence level, one must increase the size of the confidence interval to make it more likely that the true value of the mean is within the range. Therefore, the confidence interval must become wider. Wider. There you go. 11D, 12B, 13 is D, not A. If a study has low power, it is more difficult to get results that are statistically significant. Therefore, if the results are still statistically significant, even with low power, then there is likely a large effect size that makes the effect clinically significant. If the value of alpha used in the study was 0.5, then statistically significant results do not mean much. Traditionally, alpha has to be 0.05 or smaller. Eliminating choice A, concerns about toxicity should always limit the use of a drug. Eliminating choice B, statistically significant result is only of interest if it also represents a clinically significant improvement. Eliminating choice C. So the choice that they went with was D. The study had low power to detect a difference. And it would not hold the drug back. Because if it is statistically significant and it has a low power, that just means that it has a huge sample size, so that's good, that's okay. 14, they said it's D, not C. A histogram contains two peaks with a value in between. It is a bimodal distribution. The color separation of two distinct populations provides evidence that there is a qualitative difference in the data between the two peaks. Thus, the data should be analyzed according to gender. There is indeed only one mode. This is the measurement with the largest number of corresponding data. So you would also analyze two separate distributions, one for male, one for female, because they're clearly, the different peaks kind of represent the differences in male and female. I did not take a close look at this male-female differentiation. Yeah, when you see that males have a different peak than females, that does make sense to analyze the distribution separately. So D for 14, finally A for 15. All right. That is it for Chapter 12. And that's it for the Physics and Math review. Next, I think we should go into the biology. Get right into the meat of it. Thanks for watching. See you next time.